In this video, we're going to learn how to find oblique asymptotes of rational functions. A rational function has an oblique asymptote, or sometimes called a slant asymptote, if it behaves like a non-horizontal line as x goes to infinity or as x goes to negative infinity. So again, what we're dealing with here is the end behavior for a rational function. We saw in a previous video that the end behavior of a rational function depended on the degrees of the polynomials in the numerator and in the denominator. If the degrees of the numerator and denominator were the same, then we had a horizontal asymptote at y equals the fraction of the leading coefficients. That was the first situation we looked at. The second situation that we looked at was when the denominator had a higher degree than the numerator. When that was the case, we had a horizontal asymptote, but this time at y equals 0. What we'll see from our examples here is that when the numerator has one higher degree than the denominator, that's when we have oblique asymptotes or slant asymptotes. Now, when we're looking at rational functions where the numerator has a higher degree, we'll use polynomial long division to help us determine the end behavior. So let's work through some examples and get some more practice with polynomial long division. In our first example here, we want to determine the end behavior of the function f of x equals x squared plus 1 divided by 2x plus 4. When we're asked to find the end behavior, we want to know what happens to our function as we plug in larger and larger values in for x. However, the way our function is written right now, it's a little bit difficult to answer that question. So instead, what we're going to do is use polynomial long division. That way we can rewrite our fraction as the quotient plus the remainder over the divisor. So when we do polynomial long division, we start by writing down the dividend. Our dividend is x squared plus 1. Now, normally when we work with a quadratic, we have an x squared term, and then usually we have an x term before the constant at the end. Because it's missing that x term in between, we're going to need to have a placeholder for it when we do polynomial long division. So when I write my dividend, instead of just writing down x squared plus 1, we're going to write down x squared plus 0x plus 1. We have this 0x here as a placeholder for the missing x term in our polynomial. Now we draw the long division symbol, and then we write our divisor on the outside, 2x plus 4. When we do polynomial long division, we want to focus on the leading terms. In the dividend, the leading term is the x squared. In the divisor, the leading term is the 2x. To figure out what we write above here, we take the leading term of the dividend and we divide it by the leading term of the divisor. So x squared divided by 2x. When we simplify that, we'll be left with 1/2 x. Remember that another way to figure out what to write above here is you take the leading term of your divisor and you think to yourself, what do we need to multiply to this so that it matches up with the leading term of the dividend? If I have 2x, I would need to multiply it by 1/2 x so that it matches up with x squared. So our next step now is to take this 1/2 x and we want to multiply it to the divisor and we write the result underneath. So we take 1/2 x, we multiply it to the 2x, that's going to give me x squared. And then we take the 1/2 x, we multiply it to the 4, that's going to give me plus 2x. And then we're going to subtract. If we take x squared and we subtract x squared, those terms will cancel out. If we take 0x and we subtract 2x, we're going to end up with negative 2x. And then our next step is to bring down the next term from our dividend. We bring down that plus 1. Next, we repeat the process. The leading term is now negative 2x. To figure out what we write above here, we take negative 2x and we divide it by 2x. Dividing those things, we end up with negative 1. Once we have our number up on top, we take the negative 1 here, we multiply it to the divisor, and we write the result underneath. So negative 1 times 2x, that's going to give me the negative 2x. And then negative 1 times 4 gives me a negative 4. And then we're going to subtract. If we have negative 2x and we subtract another negative 2x, those two things are going to cancel out. If I have 1 and I subtract -4, the double negatives here turns this into a +4. So we have 1 plus 4, which gives us 5. Now, there are no more terms in the dividend for me to carry down, so we're done with the long division process. We now have all of our components. The 2x plus 4 here is our divisor. The 1/2 x minus 1, that's our quotient, and the 5 is our remainder. Now, from our previous video, we learned that any fraction can be rewritten as the quotient plus the remainder over the divisor. So here, for our function, we have f of x equals x squared plus 1 divided by 2x plus 4, but we can rewrite this fraction as the quotient, 1/2 x minus 1, plus the remainder, which is 5, divided by the divisor, which is 2x plus 4. Now that we've rewritten our rational function in this way, we can answer the question about the end behavior. What happens to our function as x goes to infinity or as x goes to negative infinity? Meaning, what happens to this expression as we plug in larger and larger positive values in for x or larger and larger negative values in for x? Specifically, I want us to focus our attention on this fractional part at the end of our expression. As we plug in larger and larger values in for x, either positive or negative, that's going to make the denominator larger and larger, which means the overall size of the fraction is going to get smaller and smaller. So as we plug in larger and larger values in for x, this fractional part gets closer and closer to 0. Since this component here gets smaller and smaller, as x gets larger and larger, my function f of x behaves more and more like 1/2 x minus 1. So again, as x goes to either positive or negative infinity, our function here, f of x, behaves more and more like 1/2 x minus 1. Now, if we think about the function 1/2 x minus 1, this is a linear function. So we're saying that our function f of x, this rational function, behaves more and more like this line, 1/2 x minus 1, as x gets larger and larger. So this line, y equals 1/2 x minus 1, that is our oblique asymptote. Let's take a look at our graph to confirm this behavior. So first, let's type in our function. Our function is the fraction x squared plus 1 divided by 2x plus 4. And what we found to be our oblique asymptote was y equals 1/2 times x and then minus 1. And we see here that if we were to trace our graph to the left, our purple graph gets closer and closer to that red line. As we trace our graph to the right, our purple graph gets closer and closer to that red line. So again, our graph still goes towards a line as we trace to the right, and as we trace to the left, it's just not a horizontal line. Let's take a look at another example. In example B here, we want to determine the end behavior of the function g of x equals x cubed minus 2x plus 3 divided by x squared minus 3x plus 2. Now, if we want to determine the end behavior, we need to rewrite our rational function using polynomial long division. So first, we'll need to write down our dividend. Our dividend is x cubed minus 2x plus 3. Now, normally when I have a cubic polynomial, we have an x cubed term, and then an x squared term, and then an x term, and then a constant at the end. But for our current polynomial, we're missing an x squared term, so we need a placeholder for that term. So when I write down the dividend, I would write down x cubed plus 0x squared, because we're missing that x squared term, and then minus 2x plus 3. And then we have our long division symbol, and then we'll write down our divisor outside, x squared minus 3x plus 2. Now, when we do polynomial long division, we look at the leading terms of the dividend and the divisor. To determine what goes above here, we take the leading term of the dividend and we divide by the leading term of the divisor. So x cubed divided by x squared gives us just x to the first power. Next, we're going to take this x here and we're going to multiply it to the divisor, and we'll write the result underneath. So when we do x times x squared, that's going to give us x cubed. When we do x times negative 3x, that gives us negative 3x squared. And when we do x times 2, that gives me plus 2x. And then we're going to subtract. The x cubed minus x cubed will cancel each other out. Next, we have 0x squared minus negative 3x squared. The double negatives here will turn this into a plus 3x squared. So 0x squared plus 3x squared is positive 3x squared. Then we have negative 2x minus 2x, which gives us negative 4x. Then we're going to bring down our next term from the dividend. We bring down that plus 3. And now we repeat the process. The leading term is now 3x squared. To figure out what's above here, we take 3x squared, we divide by the leading term of the divisor. So 3x squared divided by x squared gives us positive 3. So we're going to write plus 3 up on top. Then we're going to take the 3 here, we're going to multiply it to the divisor, and we're going to write the result underneath. So 3 times the x squared gives us 3x squared. 3 times the negative 3x gives us negative 9x. And then lastly, 3 times 2 gives us positive 6. And then we're going to subtract. When we subtract, the 3x squared minus 3x squared will cancel each other out. Negative 4x minus negative 9x, the double negatives turn this into a plus 9x. So negative 4x plus 9x gives us a positive 5x. And then lastly, 3 minus 6 gives us negative 3. Now, there's no more terms to bring down from the dividend, so we're done. So, in this long division, the x squared minus 3x plus 2, that's our divisor. The x plus 3, that's our quotient. And the 5x minus 3, that's our remainder. Now, remember that any fraction can be written as the quotient plus the remainder over the divisor. So, our function g of x, which is x cubed minus 2x plus 3 divided by x squared minus 3x plus 2, that can be rewritten as the quotient x plus 3 plus the remainder 5x minus 3 divided by the divisor x squared minus 3x plus 2. Now that we've rewritten our rational function in this way, we can more easily answer the question, what happens to our function as x goes to positive or negative infinity? Specifically, let's focus on the end here, the 5x minus 3 divided by x squared minus 3x plus 2. We want to ask what happens to this as we plug in larger and larger values in for x. What we've highlighted here is in itself a rational function where the denominator has a higher degree than the numerator. As we learned in a previous video, if the denominator has a higher degree, when we plug in larger and larger positive values in for x or larger and larger negative values in for x, the overall size of the fraction becomes smaller and smaller. It gets closer and closer to 0. So as we plug in larger and larger values in for x, this portion becomes smaller and smaller, so my function behaves more and more like x plus 3. So let's write that down. As x goes to plus or minus infinity, our function g of x gets closer and closer to x plus 3. And this x plus 3 here is a linear function. So our function g of x eventually gets closer and closer to a line. That's why we'll say that the oblique asymptote for our function is y equals x plus 3. Let's take a look at the graph to confirm our findings. So first, let's type in our rational function g of x. We have x cubed minus 2x plus 3, all divided by x squared minus 3x plus 2. And we found that our oblique asymptote is y equals x plus 3. Our current picture doesn't show the behavior very well, so let's zoom out a little bit. As we zoom out, we see that As we trace our graph to the left, my graph gets closer and closer to that red line. Same thing as we trace to the right. Our purple graph gets closer and closer to that red line. One thing that we observe from our two examples is that as we plug in larger and larger values in for x, our function behaves more and more like the quotient from the long division. This is because the remainder over the divisor will always go to 0 as x gets larger and larger, since the divisor will always be a higher degree polynomial than the remainder. In general, as we plug in larger and larger positive or negative values in for x, our rational function behaves more and more like the quotient from the long division. What we'll look at next is the rational function from our polynomial long division video. In example C here, we want to determine the end behavior of the rational function h of x equals 2x cubed minus 5x squared minus 7x minus 18 divided by x minus 4. We've already performed the long division for this fraction in our polynomial long division video, so let me copy over the work from before. When we performed the long division, we found that the quotient was 2x squared plus 3x plus 5, and the remainder was 2. So we can rewrite our function h of x as the quotient 2x squared plus 3x plus 5 plus the remainder 2 divided by the divisor x minus 4. If we ask ourselves what happens to this function as x goes to plus or minus infinity, we'll notice that this fractional component at the end, the remainder divided by the divisor, this will go to 0 as x gets larger and larger. So our function will behave more and more like the quotient. So as x goes to plus or minus infinity, our function h of x gets closer and closer to 2x squared plus 3x plus 5. This time, our function behaves like a quadratic rather than a linear function. And if we look at the graph, we'll see that as we trace the graph of h of x to the right and left, it'll eventually get closer and closer to the parabola defined by this quadratic function. Let's plot our function. We have 2x cubed minus 5x squared minus 7x minus 18, all divided by x minus 4. And we found that our function eventually behaves like the quadratic y equals 2x squared plus 3x plus 5. And we see here that if we were to trace our graph to the left, our purple graph seems almost indistinguishable from the red parabola. And if we're on this portion of the graph and we trace our way to the right, eventually our purple graph again goes towards that red parabola. Now, because our function h of x gets closer and closer to a parabola rather than a straight line, we would not classify this as an asymptote. So we only have oblique asymptotes when our end behavior is a linear function. And it turns out that we only get a linear function from the polynomial long division if the numerator is one higher degree than the denominator. In our current example, the numerator is degree 3, but the denominator is degree 1. It's 2 higher degree, that's why our end behavior ended up being a quadratic. But if our numerator is only 1 higher degree, then our end behavior will be a linear function, and that's when we'll have an oblique asymptote. So our general pattern is this. If the degree of the numerator is 1 higher than the degree of the denominator, the rational function has an oblique asymptote, and it's given by y equals the quotient from the long division. If the numerator has any higher degree after that, we would no longer classify it as an oblique asymptote. So in this video, we learned the circumstances that lead to oblique asymptotes, and we also learned how to find them using polynomial long division. In our next video, we'll go over some examples putting together everything we've learned about asymptotes.